Hello, dynamic students. We're continuing our discussion of particle kinematics with a brief endpoint to rectilinear kinematics, and then we will dive into cylindrical. So, as a last addendum to motion in a straight line, one direction at a time, we should add that we can move in a curved path, and we can still include that wonderful aspect of not having to consider our unit vectors change directions changing with time. If we look at our position vector as being the sum of all of its independent vector components, orthogonal components. So say rather than having a single direction that P is moving in, so its distance from a reference point in a given frame of reference is effectively its R from the origin to wherever its position is. So let's let it move in the X, Y, and Z directions simultaneously, but we're going to continue to reference its direction of motion and its position, its velocity, acceleration to the origin with respect to I hat, J hat, K hat. So we can just simply define R from the origin to point P the way we would any other Cartesian radius vector, X in the I hat direction, Y in the J hat direction, Z in the K hat direction. And since, again, with respect to a point O at the origin of a Cartesian coordinate system, our unit vectors themselves are not changing direction with time, I hat, J hat, and K hat are going to stay constant, so their time derivatives would be zero. So even though we may have some straight line motion in all three directions, if we consider each one separately, which we can when we look at our radius vector in terms of its components. So we can go back and invoke the idea that the derivative of a sum is the sum of the derivatives. We can look at the velocity, or ROP vector dot, which is the velocity of point B with respect to the origin, as just our speeds effectively in the X, Y, and Z direction, and acceleration as the second time derivative of our positions X, Y, and Z. Again, we are able to make these simple expressions because our unit vectors are not changing with respect to our reference frame with time. If I hat, J hat, or K hat had a non-zero time derivative, we would have another expression there. So I won't go through the example for that, but basically you can step through it. It's another rectilinear kinematics, except with motion occurring in all three orthogonal directions without the unit vectors changing. Okay, so now we're going to launch into a second coordinate system. Most of you who've done some calculus or some physics, maybe some advanced algebra, are probably familiar with the fact that it's really convenient to express certain types of geometry relationships that are axis symmetric in cylindrical coordinates. So instead of an X, Y, Z, or I hat, J hat, K hat Cartesian position expression, we're going to have an R theta Z. So we're going to go a distance R in a plane that is parallel to the XY plane, or that's perpendicular to another plane. We're going to rotate a certain angle theta around a point that's our central axis, and then we'll move up in a straight line. So R theta Z. So now we have new unit vectors. So instead of I hat, J hat, K hat, we have E theta hat, E R hat, and K hat. So we're using the E's as a denotation of a unit vector in whatever coordinate system. So we can look at kind of at cylindrical and Cartesian superimposed. We have our Cartesian IJK, and then we've got an R at an angle theta from our x and then position going up in the z to get our ROP, which is effectively r in the r hat direction plus z in the k hat direction. So I can define the position of point P in cylindrical coordinates as r er hat z k hat. Notice we have a theta rk coordinate system, but my position doesn't include a theta. The r effectively already contains it. And what we're saying is I'm going to go a length of r in whatever direction my r unit vector is pointing. Now the direction of that unit vector r might have an awful lot to do with my unit vector theta and my value of theta at the time, but just to express position, it is what it is. And we're going to see that theta comes in when we start taking time derivatives, but at this point our position expression only includes r and k, or r hat and k hat. So our radius coordinate and our z, our height coordinate. Okay, let's start taking time derivatives now. So if I want to get the velocity of P, it's moving along on this path. And rather than expressing it in ijk, I want to express it in r theta k. Because I don't know, maybe it's going to move in a circle at some point. So let's just start taking time derivatives. So we've got two products. We've got a sum of two products. So we're going to just apply our properties of derivatives of a product and a sum. So we're going to start with our first term. So we're going to take the time derivative of r and get r dot, multiply by our unit vector in the r direction, and then I'm going to add to that r times the time derivative of the unit vector in the r direction. And then I'm going to add to that basically z dot times k hat, and k hat is not changing with time. Okay, so I don't have to have a z plus k hat dot because k hat, I know that that isn't changing with time. R hat, er hat, the unit vector direction in r is changing with time though, because if you imagine this point moving along this path, this r is going to have to track around to follow it, and it's going to be moving. This r vector is going to be moving, that you see that's down here on the I hat, j hat, or the xy plane. It's going to swing back and forth to follow the projection of this point that's moving along in space somewhere. So it's going to be the direction that this unit vector r is pointing is always changing. The k hat direction is up, is always up in this case, but the r hat direction is always changing with time, or there's a very good possibility it might be changing with time. So we're going to need to find a way to express what is the time derivative of the r hat vector in Cartesian coordinates. Can we write a general expression for it, and can we relate it maybe somehow to the theta hat unit vector, and see if there's some general relationship between them that then we can leverage when we're going forward in trying to describe motion with cylindrical coordinates, which is really handy in a lot of cases. Well, as it turns out, we are actually going to use Cartesian expressions to relate the rate of change of the r hat unit vector, the direction of r, to the direction of theta at any time. So let's use and we're going to use the Cartesian coordinates by expressing some geometry. So let's just use some real simple geometry. Let's focus on the xy plane, and let's take a look. We've got our r vector, and here's our here's our r hat, e r hat. So here's our r unit vector, and at this point our e unit vector, our theta, e theta unit vector is pointing perpendicular to our r. So here's our two cylindrical unit vectors. So we can relate those with just some simple trig, some right triangle trig. So our e r hat is going to simply be cosine theta times 1 plus sine theta times 1 in the Cartesian directions. Now normally we don't want to be mixing up Cartesian and another, but we're going to use the Cartesian to give us some relationships between the r and the theta. Okay, so we're kind of referencing through Cartesian. Okay, so let's take the time derivative of this expression. So we have the r hat unit vector. Now I'm going to take the time derivative of it because that's what we were looking for up here. Okay, so we take the derivative of cosine theta and we get negative sine theta, j hat, this should be I hat, plus take the time derivative of sine and we get cosine, and that's j hat. This should be an I hat. I'm going to correct that right here to make it a little easier to see. And then, of course, to complete the derivative, we have to take the time derivative of the argument of the trig function, kind of applying a bit of the chain rule there. So we multiply both of these by theta hat, theta dot, so that's d theta dt, because we're taking a time derivative, that's what the dot means. Okay, let's go ahead and express, while we're at it, not the time derivative, but just the plain old theta hat expression in terms of our Cartesian coordinates. So now we're looking at this vector, theta hat. Well, we can write basically a similar expression for theta hat that we did for r hat using another trigonometric expression. Basically, in this case, we would look at this direction being the hypotenuse and make a different right triangle. And as it turns out, our theta hat direction is negative sine theta x direction plus cosine theta y. Well, if you compare this, and this is again just using some trig. I don't have the triangle written out shown on the diagram, but you can actually draw it just looking at this e theta and then make a right triangle and look at the components that would be in the I hat and j hat directions. So our position unit vector theta is negative sine theta I hat plus cosine theta j hat. Gosh, that looks an awful lot like the first time derivative of our r hat unit vector. The only difference is that time derivative of theta, which is a scalar function. Okay, so we can relate these two now and say, well, my theta unit vector in cylindrical, my theta hat, is equal to the first time derivative of my r hat, my radius unit vector, divided by the time rate of change of theta. So now I have a relationship between a unit vector that isn't going to change with time in this expression and one that is changing with time. So basically I can say that my r hat first derivative of time is equal to my theta hat times the rate of change of theta with time. So I can drop down, differentiate with time, and a lot of this is rewritten. So I started with my radius vector O to P is r er hat plus zk hat. So there's my radial component and my height component. I differentiate with time, r dot r hat plus r hat dot plus z hat k hat, or z dot k hat. It's a lot easier to see than read. Now I add my relationship between my theta unit vector direction and my r unit vector first derivative with time, which in this case is these two. I can relate because we've got the negative sine theta I cosine theta. So we look at where do the Cartesians match. So they kind of draw a big equals between the cylindrical parts of them. So we're using Cartesian trig expressions to relate the time derivatives of the unit vectors of our cylindricals so we can get a full expression for our cylindricals. So again, from the previous page and from these two expressions, we can say, okay, first time derivative of my r hat, my radial vector in cylindrical, is my non-derivative, just my plain theta hat, times my scalar d theta dt. Great. Now I can plop that in and I have a full expression for velocity in cylindrical. So I can express the velocity of that point P that's wandering around in terms of r theta z and scalar expressions for r and time derivatives of theta and z. So r hat, theta hat, z hat with some scalars, multiplying them. Okay. Obviously, we might want to get an expression for acceleration because ultimately that's what we're going to have to use to relate to force. Because eventually we're going to want to make the jump to kinetics, get an expression for force, and then say, wow, what's the resultant change in our motion with time? Okay, no problem. All I have to do is take another time derivative, right? We can do that. Okay, so we're going to go back to our rules for taking derivatives of sums and products, and in this case we've got scalars multiplied by unit vectors, which are pretty easy. So I'm going to apply those rules, and I'm going to say the acceleration of point P with respect to O is going to be the first time derivative of this expression up here for velocity. So I'm going to go taking the time derivative term by term. So I have a product here. So I've got dr dt times unit vector r. So first I'll do another derivative of r. So I have r double dot times unit vector of r. Then I have r dot times er hat dot, which I've already defined as d theta dt times the unit vector in the theta direction. Okay, so that's first term down. Now I look at the other term. I have three terms all multiplied. So I get to apply the derivative of the product to all the terms. So I'm going to take the time derivative of r, multiply by the other two. Then I'm going to take the time derivative of theta dot, and then I multiply by the other two. And then I'm going to take the time derivative of the theta unit vector and multiply by the other two. Okay, so the first one's pretty easy. So the derivative of r with respect to time is just r dot. So I end up with r dot theta dot in the theta hat direction. No problem. Now I'm going to take the time derivative of theta dot. No problem. I get theta double dot. So d squared theta dt squared times r, again, pointed in the theta hat direction. Okay, now I get to the tricky part. Now I got to take another time derivative of a unit vector, and this time it's the theta hat unit vector. So now I'm going to go back to these other trig expressions. So I'm going to say, okay, if I could use a cosine I hat sine j hat type of expression to relate the r hat theta hat time derivative, I can do it vice versa. So I'm going to say, great, I can express, again, r hat, theta hat. This time I've expressed theta hat. I'm going to take the time derivative of theta hat. So sine theta, the derivative of sine is cosine. I had a negative. The negative carries down. The derivative of cosine is negative sine, so now I have a negative sine. So I have negative across the board. And then, of course, I take the time derivative of the argument of the trig function. I get a theta hat. So, or excuse me, theta dot. D theta dt. And this is the theta hat dot. So time rate of change of the unit vector in the theta direction. So let's compare that to just plain old unit vector in the r direction. I got a cosine theta I, got a sine theta j. So basically it's the same thing as this, except we've got a negative sign and we've got this theta hat going on. So I could basically express my theta hat, my unit dot, so my time rate of change in the theta unit vector direction is negative theta dot times my radius vector, unit vector direction. So effectively, the time rate of change of those cylindrical coordinates is the other cylindrical coordinate. It's that direction. So if you're looking at your radius vector and saying, what is the direction that says this is how my radius vector is changing? It's the theta hat unit vector. If I'm saying, what's the direction of change of my theta vector? It's the r hat unit vector. They just swap. Except in each case you multiply by your d theta dt scalar, and then in one case you have a negative sign. And so just remember, you're using Cartesian coordinate geometry to establish the relationships between these cylindrical quantities, and it's just right triangle trig. So just draw it on an xy axes here and look at the right triangles. We have r as a function of I hat j hat drawn. We could do the same thing with a theta vector and draw the same ones, but we end up getting these expressions, or we get the r hat, theta hat, and then we take the time derivative, and then we just notice, hey, you know, each one of these, as you go diagonal in this bundle of expressions, you can substitute one for the other. So now we have a way of expressing the time derivatives of those unit vectors in terms of a unit vector that is not a derivative. Because that's what we really want. We want to just take a scalar, whether it's a time derivative of something or not, and aim it in a unit vector direction. We don't want our unit vectors changing when we're trying to apply numbers and see which way things are lined up. We had to accept the fact that they were changing direction when we took the original time derivatives, but having done so, now we'd like an easier way to express them that just says, okay, what direction is this really going in when all is said and done? So that's what we've done. So that is, we are down to this expression at the end of the day. So we had our r times theta dot times theta hat dot, and for theta hat dot we're going to get a negative d theta dt in the r hat direction. So we'll substitute that there, and it ends up going down here. So we end up with one term with a negative, and we have squared. Okay, so this is not a double dot. This is the first time derivative of theta parentheses squared. So our acceleration of point P with respect to O in cylindrical coordinates is second time derivative of r in the r hat direction plus 2 times first time derivative of r times first time derivative of theta aimed in the theta hat direction plus r times the second time derivative of theta aimed in the theta hat direction. So we got two things aimed in the theta hat direction there, minus r times first time derivative of theta squared aimed in the r hat direction plus second time derivative of z aimed in the x and the k hat direction. So we have two things in the r hat, two things in the theta hat, one thing in the k hat. So we can group terms and take a look at what's aimed in what direction. So not surprisingly, we have a term that's basically the second time derivative of the radius position aimed in the r hat direction. So that's d squared r dt squared. Not surprising. So that's literally the rate of change of r with respect to t. But we've got this other term that's the radius, the position at any time, the radius position magnitude times the square of the rate of change of theta. So that's what's known as a centrifugal component, and it is pointed opposite. It's pointed back to the center in the r hat direction. So that's something that you've probably encountered that's known as centrifugal acceleration. So it is something that must be satisfied to keep something going on a curved path. If it's not satisfied, something will not go on a curved path and it'll go flying out straight. Okay? And we've got similar terms in the r hat, or excuse me, the theta hat direction. We have basically the second integral, or excuse me, the second derivative of theta with time times the radius. So something that's really specific to theta. And then we've got something over here that's kind of two velocity components of r. That's effectively the reflection of what we had going on here. So theta hat and r hat acceleration components kind of talk to each other. They're interdependent. So that's why we have expressions of each in the other. Z, the k hat direction, because k hat never changed with time, it's not throwing out all these other terms. So you might ask yourself, why in the world would I use such a complicated expression for acceleration when I could just use, x double dot I hat plus y double dot j hat plus k double dot or z double dot k hat? Because the answer is because a lot of motion is really, really simple to express in cylindrical or sometimes even spherical, and the actual functions for r and theta with time are really, really simple, or they're very easy to visualize with respect to applied forces when we use these expressions. So we have a little bit more complexity in our basic expression for acceleration, and come on, it's not that complex. There's a couple extra terms with some pretty simple geometry that we use to derive it. Now, there's nothing wrong with taking this expression and writing it down somewhere. You don't have to go through this entire derivation every time. So you can write acceleration, velocity, and position in cylindrical in terms of r hat, theta hat, k hat, and just use them in problems. That's fair. Once you've derived it, you can use it. But you'll find that these actual time-dependent expressions can be super, super simple if you have something that's amenable to that coordinate system, which is, of course, the only reason you'd use it. So general observation, the derivative of the unit vectors, r hat and theta hat, are perpendicular to the vector being differentiated. So that's kind of the rule. Time derivative of r hat's going to be going in the theta hat direction. Time derivative of theta hat's going to be pointing in the r hat direction, so they pull each other around is another way of thinking about it. Okay. we'll launch into a little bit more explanation here, and then we'll end before we kick into some examples. So just another little geometrical look of why we have the time derivative of the unit vectors being kind of opposite to one another. Why does the time dependence of our radius unit vector depend on the time dependence of a theta coordinate? And why is it going in that direction? We can, I'm going to try to blow this up a little so we can see the geometry. We can make a little dt change in position. So we're not going to look at the k hat component. We're just going to look at the two r theta position components of motion. So at time 1, your p is here, so you could express the position as r in the r hat direction, which is pointing in this direction at this time, and then some delta t later, you can describe the position by this r vector, which is pointing in the new r hat direction, which is now being described by a theta plus delta theta, whereas this one was just a function of theta. So, your delta theta is representing your time-dependent change. Delta theta, delta t, we're kind of setting up for it. So let's make a little triangle here, and let's do some vector addition. We can say, all right, our er hat at theta plus delta theta is our er at theta plus is delta er, right? So we can do vector addition. We can go from here, and we can add these two vectors and get this resultant vector. Okay, so this er changes with time, and in fact it shrinks down with time, and it shrinks down with theta. So as this delta theta, which is this delta theta, gets smaller and smaller and smaller, this gets smaller, and these two vectors get closer together. So let's just kind of sum all this up and write it in terms of the definition of derivative. So if I was gonna take the limit of this delta going to 0, so I get a d er hat d theta as this ratio, the deltas shrink to d's. I would be looking at the limit as this delta theta goes to 0 of that vector minus that vector divided by delta theta. So the er position at time 2 at theta plus delta theta plus minus the starting position divided by the change in the angle. So this is literally the definition of derivative for that derivative. Can't argue with that. So looking at that describes what we're seeing in the figure. Okay, so we can explain everything going on with this geometry that's describing our motion as a change, as a derivative change in our hat with respect to theta. Okay, so delta er direction is effectively the e theta hat direction as theta goes to 0. So you can see if you're looking at this delta er, we're going to go back and do a little scribbling. This was the r hat direction here. It's kind of hard to draw. Perpendicular to r hat is e hat. So delta er, the change in the r hat unit vector, is the theta hat unit vector. So you can see it kind of geometrically, graphically, what we described with the trig functions going back through Cartesian. Now we've kind of said the same thing, by just visualizing the change in the two position vectors with a change of time, and that change of time involving swinging around of our theta angle. So that kind of has shown that, yeah, the theta hat direction is the direction of the change of the r hat direction. And furthermore, we can look at the magnitude of this change being described geometrically with a sine of the half of the theta angle, and then that approaching 1 as theta approaches 0, our small angle approximation goes to 1. So in that case, we've shown that we keep a unit vector. So the direction of that delta r is the theta hat. The direction of the delta r hat is the theta hat direction. What's the magnitude? Well, as we start shrinking that delta theta down to 0, this goes to 1. So we end up with the change in the r hat unit vector with a change in the angle, which is the change in time, because our angle is swinging around with time, is going to be 1 in the theta hat direction. And so we can even express this with a chain rule now and say, okay, change in the theta hat, the r hat with theta times change in the theta with time. We're going to get the change in the r hat with time. So this term here, we just said was that. So we apply the chain rule, and we know that this term is theta dot. So now we're basically back to our expression that we derived with the sine and cosine theta with our Cartesian trig expression before. So this is just sort of an analogous way of looking at the mutuality of those unit vector directions. Our r hat changes in the theta hat direction, and our theta hat changes in the r hat direction with a minus sign. And then in both cases we multiply by the scalar rate of change of theta, which is tracking the change in time. So mutual, as it turns out, this mutual orthogonality of any vector and its time derivative is a property that's of all constant value vectors, like unit vectors are all a constant value of 1. So we could apply this to any unit vector in any system. Its rate of change is going to be inevitably pointing in the direction of another unit vector in that same system, which we'll leverage later on, so we're not having to derive everything from scratch. So we're going to end this lecture. It's gone on a bit long with a lot of theory, and then we'll pick back up and apply it to a couple of problems. You can see the first setup. We've got this rotating disc, and we're going to sling a pin out through the slot as it rotates and describe its spiral motion. So if that isn't cylindrical in nature, I don't know what is. So stay tuned, and we will apply our awesome cylindrical coordinate expressions for position, velocity, and acceleration to a cool problem.